So in the last lecture, we were discussing uh, titrations with acids and bases, and now we're moving on to a different type of equilibrium, in which we're looking at the equilibrium of sparingly soluble salts, or stuff that we covered last semester that we said was just not soluble. And if you remember last semester, we treated these things essentially as stuff that was completely insoluble. The reaction went to completion. In reality, everything has an equilibrium constant, and these have an equilibrium constant that is um, substantial enough that we want to consider it, at least for the ions that are going to be present in solution. And we'll discuss, like we are in Lab 8, how that solubility can change based on Le Chatelier's principle and the shifting of that equilibrium. And so we recognize that the ions are still dissolving, and even though that we have a precipitate present and the solution is what we call saturated if that precipitate is present. And the ions are just basically crystallizing and dissolving at all moments at equilibrium. It's just that the rate of crystallization is occurring at the same rate that it's dissolving. And so we don't see anything change to our eyes. Now, if we're to look at how we'll focus on calcium fluoride first. And so if we write the reaction between calcium fluoride and insoluble salt, we end up with Ca2 plus and plus 2 fluorides is what it dissolves into. Now, if we write the equilibrium constant for that, it would be the K equals calcium times fluoride squared. And you notice that the calcium fluoride is not present because it's a solid, and we leave it out of the equilibrium constant. Now, you see another subscript there because we're throwing in another K at you. And this K is the solubility product. And the solubility product is just, it's like we have Kf, we have Ka, Kb, Kc, Kw, all kinds of different Ks. This is the one that pertains to insoluble salts. We use the Ksp, or the solubility product. So, when it comes to measuring the sort of KSP, if we know the amount of each of the ions that are present, then we can calculate what the KSP should be in a saturated solution. You'll hear me saying saturated solution. That just means there's some salt present. So it's now in equilibrium if some salt is present. And so if we had some saturated solution where we have some calcium fluoride sitting on the bottom, and we're able to ascertain what the calcium concentration is, and in this case we're saying 2 times 10 to the minus 4 molar, and with fluoride we're saying 4.1 times 10 to the minus 4 molar at 25 degrees Celsius. If we can find those concentrations, then actually figuring out what the KSP is not too hard. All we have to do is write that expression for our solubility product, and we plug in our values for the different equilibrium concentrations, and then we end up with a value of 3.4 times 10 to the minus 11. Okay, so let's take a look at this clicker question, and it basically asks you which of the following solubility products is not written correctly. And so the way that we should approach this is probably just going ahead and writing all the equations or reactions for each of these equilibria, and then determining which one isn't consistent with what we see for the KSP that's written. And so with the first one, we're looking at silver phosphate. It has 3 silvers, so it goes to the 3 silvers plus 1 phosphate. The second one, this one is a little tricky because you might not remember the polyatomic cation, which is just mercury 2 plus, so that's a polyatomic cation, and sulfide, so it breaks into those 2 pieces. This next one is just a monatomic cation of mercury, and so just this mercury 2 plus, and it breaks into plus 2I minus. And then lastly, we have silver sulfide, and this doesn't have a polyatomic cation, so it just breaks into 2 silver pluses plus S2 minus, or the sulfide. Which one of those is inconsistent? So if we look at the first one, we can see immediately that the silver here has a 3 in front of it, and we also have a 3 here, so that looks okay. If we go ahead and look at the phosphate, it has a 1, and we see a 1 up above there, so we should be good there. This one has a 1 in front and without a coefficient or some exponent there, we assume it's 1, so that looks consistent. The sulfur or sulfide again is 1. Mercury, we have a coefficient of 1, and that's consistent with what you see there. And with iodide, we have a 2, and that's what we see up top there is the exponent. The one that is not consistent is this one is broken up into the wrong ion, and so this shows basically just a, we should get a silver squared, silver plus squared, and instead they have this polyatomic cation, which does not work. And so that one is the incorrect one, and so we label that one as our answer for this particular problem. Just looking at some KSP values for the ionic compounds that we have, the one thing I wanted you to take note of is the fact that all of these are incredibly small. The one that is the least small is still 10 to the minus 5 on this. And it goes all the way down to 10 to the minus 33. So these are incredibly small values. This should indicate to you that these are favoring the reactant side heavily, very heavily. And so these things are sparingly soluble, and for all intents and purposes, if you were just adding the two, you'd expect most of it to just go to completion. And so sometimes just writing the precipitation reaction, which is the opposite of that solubility product, you would write it with just an arrow instead of an equilibrium sign. So one of the important things to characterize with a lot of different salts is the molar solubility. And so in this particular problem, it asks you to calculate the molar solubility of magnesium fluoride in water at 25 degrees Celsius, and it gives us the reaction below. Of magnesium fluoride 2 plus breaking into, or magnesium fluoride breaking into magnesium 2 plus and 2 fluorides. The definition for molar solubility is just the amount of compound or salt that will dissolve per unit volume of solution. And so if we find some compound that has a molar solubility of 3 times 10 to the minus 5, then what that indicates is that we can mix up enough solution, but once we get to a concentration that's greater than 3 times 10 to the minus 5, we're going to start seeing a precipitation occurring. And so that is the essence of what the molar solubility is and why it's an important thing to characterize for many salts. Now, molar solubility isn't too hard to actually solve for. It's always the value of X from our ice diagram, and it's commonly denoted as just S. So if we wish to solve it for this particular problem, we need to have a KSP, and that'll either be given to you or you'll be able to find it in a table for this type of problem. And so we next want to set up our ice diagram. We're assuming we start with 0 of the different ions that are present. We're not looking at a common ion effect or something like that. So we're just assuming we have both ions are not present. We have 0 for their initial concentration. Because of their stoichiometry, magnesium gets an X for its change and 2X for fluoride. And then if we look at equilibrium, we have an X and 2X when we add those two. So now if we go ahead and write the KSP value that we'd expect there, we'd end up with the magnesium and then fluoride squared. Now if I go ahead and plug in my equilibrium values for X, then I end up X times the quantity 2X squared. That gives me 4X cubed. Now I'll equate that 4X cubed to KSP and I'll rearrange to solve. So that gives me X is KSP over 4 raised to the 1/3 power. Or we could equivalently say that it is KSP over 4 to the cubed root. Those are equivalent mathematical expressions. So just be familiar with both of those, and I would encourage you to try typing those into your calculator, because that's something that sometimes students have a little bit of issue with just when they're first working on these problems. So make sure you're familiar with how you put those types of maybe cubed roots or roots to the 1/5 or anything of that nature, those more complicated exponents into your calculator, and make sure you're getting consistent answers with what we're getting so you're squared away on that, okay? So if we go ahead and calculate, our X value is 2.6 times 10 to the minus 4, and so that also equals our magnesium concentration, and twice that is just the fluoride concentration that you see below. And remember, X is also sometimes commonly referred to as just S because it is just the molar solubility of this salt. So this means if I go ahead and make a solution of magnesium fluoride, then I can start putting in magnesium. I can put in enough magnesium fluoride till I get to a concentration of 2.6 times 10 to the minus 4. And at that point, I'm going to start seeing precipitation. All right, so let's look at calculating the molar solubility of silver chloride at 25 degrees Celsius. So just another problem very similar to the last. So we need the KSP value again, and so we get 1.8 times 10 to the minus 10. I set up my ice diagram. It's a little bit simpler because our stoichiometry is just creating one silver and one chloride, so it's all X's over there. KSP is just going to be equal to the silver concentration times the chloride concentration. If I plug in my X values, I end up with that X squared that you see right there. Now, if I solve for X, it's the square root of KSP, and that gives me 1.3 times 10 to the minus 5. And then that equals the silver concentration and the chloride concentration at equilibrium. And also remember that that's the molar solubility of silver chloride. So this clicker question focuses on tooth enamel, which consists of hydroxyapatite. And so it is a bunch of calciums, a bunch of phosphates, and a hydroxide. It has a solubility, or a molar solubility, of 5.2 times 10 to the minus 5. So it asks, what is the KSP for hydroxyapatite? So if we were to set up a problem like this, then it's a little bit backwards, right? It gives us basically S, which is also X. So if we set up the ice diagram, which then generates that KSP and X relationship, then we should be able to plug in our value for the molar solubility into that X, and we should be able to solve for the KSP. So I write out the equation here for the dissociation of this particular salt into all of its constituent species. And then I set up my ice diagram, and it's a whopping mess. We end up with 5X for calcium, we end up with 3X for phosphate, we end up with X for hydroxide under the change row. You'll notice the initial concentration is 0 for all of them because we're just trying to figure out after we put that in a solution, what's going to happen, what concentrations will we end up with. And so when we sum them, we just end up with the 5X, 3X, and X. So if we solve for the KSP, it's going to be 5X to the 5th, 3X cubed, and then X. That becomes quite a big number. It becomes 8.4375 times 10 to the 4 times X to the 9th. Now, if we go ahead and solve that by plugging in the value for X that we have up above, the solubility, we end up with 2.3 times 10 to the minus 34. A very small number, and it also corresponds to B in the answer. It's very fortunate for us that it is such a small number, or our enamel and our teeth would dissolve. I don't think I mentioned it here later, so I'll mention it now. If you ever use fluoride, or you get fluoride treatment at your dentist, what you're doing is you're basically replacing that hydroxide with a fluoride, and that's actually less soluble than the species that we have here. And so it helps your teeth enamel stay stronger than it would with just hydroxide. So this clicker question asks us, which of the following silver salts is least soluble in water? And so it gives us a number of KSPs. But we have to be very careful just going off the KSPs, because the solubility product is something that we solve for when we use our ice diagram, and the coefficients matter on that. And so if you don't see that right now, hopefully after we go through each one of these, you'll see that it matters that we actually calculate it out using the equilibrium constant for each one of these. And so all we're going to do is we're going to calculate X, or the solubility product, for each one, and we know that the one with the smallest value of X is going to be the least soluble. So for the first one, we see that silver is going to break up into 2 pieces, and then the sulfate is going to break into 1. So that's going to give us, for the silver, a 2x, and we raise it to the square, to the second power. And then we just have the x there for the sulfate. That's going to give us 4x cubed. If I go ahead and solve for that, for x, I end up with 1.5 times 10 to the minus 2 molar. Solving for the second one, silver iodate, that's just going to end up breaking into 2 pieces, the silver and the iodate, and it's just going to end up with an x squared value. We go ahead and do the square root of that, 3 times 10 to the minus 8. We end up with 1.7 times 10 to the minus 4 molar. Going to C, which is the silver chloride, again, just breaks into two pieces. We know we're going to get an x squared from our ice diagram for that one. And then I go ahead and solve for x, and I end up with 1.3 times 10 to the minus 5. Going to D, we have 1.1 times 10 to the minus 12 for its KSP. We know that the chromate is going to break into one piece, and the silver is breaking into two. So we get a 2x squared times x, which gives us 4x cubed. Solving for that x value, we end up with 6.5 times 10 to the minus 5 molar. And for E, we have silver phosphate that breaks into 3 silvers, and then it breaks into just 1 phosphate. So that ends up with the quantity 3x cubed times x, which gives us 27x to the 4th. So solving for that one for x, we end up with 4.3 times 10 to the minus 5. Now, if we were to just go look at that, I might be inclined, and I bet some students that aren't paying attention by the time we get to the exam, they'll look at this and they'll go to the KSP with the smallest value. So they'll pick E. But is that really the smallest value? If we look through here, we have 10 to the minus 5 as our smallest exponent there. And so we have it between 1.3, 4.3, and 6.5. And it goes to the winner, C. C has the smallest molar solubility for this particular problem and will be the solution that we're looking for here. So make sure you're not basing it off of just what the KSP value is. You have to solve for the molar solubility to discover which ion is actually, or which salt is actually least soluble. Okay, so common ion effect, and we talked about a little bit about the common ion effect and how it affects the pH in a solution. Here we'll talk about how it affects the solubility of our salts. And so let's go ahead and look at calculating the molar solubility of magnesium fluoride. And we're going to do it in 0.1 molar of sodium fluoride. So notice fluoride is common to both of those. And we're doing it at a temperature of 25 degrees C, and the KSP is 7.4 times 10 to the minus 11. Solving this, setting up our ice diagram, notice the big difference here is that where we initially always had both of those quantities in the top row under initial concentrations is 0. Now, because we have the sodium fluoride present, one is labeled as 0.1. Putting in the change, because we still know the reaction is going to the right, we get X under magnesium, and we get 2X under the fluoride. We go ahead and plug in, we sum those two rows up above, and we end up with the X under the magnesium and 0.1 plus 2X under the fluoride. If we go ahead and solve this, again, we can make our approximation. Remember, the approximation worked well before we started adding common ions, and common ions serve to suppress the dissociation in this aspect, or in this particular problem. And so if that's the case, then we should expect X to be even smaller and our approximation to be spot on. And so we go ahead and plug that in, and we end up X times the quantity 0.1 squared. We end up with 0.01 X equals KSP. Rearranging for that, we end up with an X value of 7.4 times 10 to the minus 9 molar. Now, without the salt, we get a molar solubility of 2.6 times 10 to the minus 4 molar. So it's quite a bit more soluble if we don't have that common ion present. But with that common ion present, it really, really wants to precipitate, and it really suppresses any dissociation that might have occurred. This is just basically another manifestation of Le Chatelier's principle, like anytime we talk about common ion effect. We're adding products, and so we expect it to shift to the reactant side and decrease the solubility of the salt. This just special occurrence is just given a special name of common ion effect. Here's an example of the solubility of magnesium fluoride as we add more and more sodium fluoride. And what you'll notice is as we go up to even 0.12 molar of the sodium fluoride, it drops 4 orders of magnitude in solubility. So it decreases quite substantially as a result of the presence of that fluoride. So another factor that can affect our solubility of our ions, and something that we are investigating or will be investigating in Lab 8, is the solubility of these salts and the pH of the solution. If one of the products of the insoluble salt is an acid or a base, then the addition of a acid or a base to that solution can then react with it, and it could potentially pull it out of solution, and then that's going to change the solubility of our insoluble salt. So let's take a look at an example of that. So we'll start with something like calcium carbonate, and hopefully you recognize that the carbonate anion is a weak base. And so if we put an acid in this solution and we have a weak base present, we know from all of our discussions about the reactions of acids with bases, we know that it'll pull it out of solution and it'll protonate that carbonate ion. So let's look at the example of just that. So the H3O plus reacting with the carbonate to produce bicarbonate plus water. I write the KSPs there's on the right hand side. It's 5 times 10 to the minus 9 is the solubility product for the calcium carbonate, and the neutralization reaction between the carbonate and the hydronium ion is 1.8 times 10 to the 10. If we go ahead and look at what we'll get as we sum those two reactions, we'll end up with the calcium carbonate plus the hydronium yielding calcium ion, bicarbonate, and water. And all of a sudden, when we add those two, we get a K of 89. And if you remember, when you have a equilibrium of 89 or something that's close to 1, then that says it favors the products and the reactants. It's not really pushed too much one direction or the other with a value of 89. And so this salt becomes very, very soluble relative to what it was, simply because we are adding some acid. This calcium carbonate, you may know, is limestone. And one of the reasons, one of the most amazing cave structures in the world are often limestone, is because we have CO2 in the air that can dissolve in the water. This can then will produce some acid, and that acid can then react with that carbonate, removing it and making the calcium carbonate much more soluble. So it makes the water basically this great solvent for dissolving that calcium carbonate or that limestone. And it's just another manifestation of the Le Chatelier's principle. So given what we know now, we could probably make a good estimate on whether salts or insoluble salts are going to become more soluble in the presence of an acid. So let's take a look at several salts and decide which ones become more soluble. So we have silver cyanide, lead iodide, aluminum hydroxide, and zinc sulfide. So if we look at those, which ones have weak bases present? That's what we're looking for if we're talking about becoming more soluble in an acidic solution. Silver cyanide, that should ring a bell because hydrocyanic acid is something that, or hydrogen cyanide is a weak acid, and cyanide is a weak base. What about the lead iodide? Hydroiodic acid is a strong acid. Iodide is not a weak base. And so that one, we don't expect it to be affected. Now, aluminum hydroxide, that one should be pretty evident because hydroxide is something we get as a product of this dissociation. And so, yeah, that one is going to become more soluble. Zinc sulfide, that one might be a little bit more tricky to remember, but remember that it is a weak acid to hydrogen sulfide, and so the weak base is the sulfide ion, and so that should become more soluble. So all we're looking for in this case is if there is a base present, then adding an acid will effectively remove that base from solution, and then it should just shift the real equilibrium to the product side. And in turn, that's what's going to make the salt more soluble. And you can see there for calcium carbonate, depending on the pH, it becomes quite soluble. Down to a pH of 5, it goes to less than 0.1 as its solubility. But when we get to a basic pH of 12 or so, it is quite insoluble with a solubility that is less than 10 to the minus 4. Okay, so let's take a look at another type of reaction that can remove the product from our solution and therefore push the reaction to the product side. So for example, what we're going to look at here is the reaction of silver chloride, and it's a very insoluble salt as we discussed. It has a KSP of 1.8 times 10 to the minus 10. Well, silver has another reaction if you place ammonia in solution. It can complex with this ammonia, and two ammonia can attach to that silver, and we end up with an equilibrium constant for that. That is 1.7 times 10 to the 7, strongly favoring the product. So if you put ammonia in there, it wants to grab a hold of that silver. And so if we look at the sum of those two reactions, the silvers will cancel out. And what we'll be left with is silver chloride plus 2 ammonia yields the complex plus chloride. And if we figure out what the new equilibrium constant for that reaction is, the equilibrium goes to 3.1 times 10 to the minus 3. That is a much, much bigger number than what we had before with the 1.8 times 10 to the minus 10, and therefore means that the silver chloride is much more soluble by way of that Le Chatelier's principle and the fact that we're pulling the silver out of solution via that complexation with the ammonia ion or the ammonia molecules. The Kf is yet another one of these equilibrium constants. It corresponds to the formation constant. And so this just represents the equilibrium constant when we form complex ions in solution. So if we look at the solubility of this solution, looking at silver with ammonia, you can see that if you just put silver chloride in pure water, it's quite insoluble with a solubility product or a molar solubility of around 10 to the minus 5. But once we complex it with enough moles of ammonia, it gets all the way to a smaller value than 0.1, or to a larger value than 0.1, I should say. And so it becomes quite soluble in the presence of that ammonia. Here you can see basically a silver chloride solution on the left, and we have a lot of silver on the bottom. But what you see, you put a little ammonia in there, and on the right-hand side, because of that complexation, and you can see in these illustrations in the drawings here, you can see basically it's showing the ammonia molecules, these guys right here, complexing around each of those silver ions. So in each case, we have just basically two ammonias coordinating with each of those silvers, making it more soluble. So one more factor that we want to talk about is amphoterism. And we've discussed a little bit about amphoterism when we discussed water. If you remember, if something is amphoteric, we're saying that that species can either act as an acid or a base. And in that context, we talked about water being able to act as an acid or a base in different conditions. So if we look at aluminum hydroxide, it might be pretty evident to you that the hydroxides that are present in that aluminum complex or the aluminum hydroxide salt are going to be able to react with the hydronium ions, and they're going to be neutralized, freeing that aluminum of the hydroxides, leaving you with just aluminum 3+ and now 6 waters. What might be less obvious is that aluminum hydroxide can also act with hydroxide. And in the presence of hydroxide, we can attach one more hydroxide to the aluminum hydroxide species, giving us 4 hydroxides surrounding that aluminum. Now, that's probably better understood as an acid-base reaction in the context of the Lewis acid, Lewis base sort of nomenclature that we looked at the very end of chapter 14. So if this species is very insoluble, and if you remember back to that table at the very beginning of this lecture, aluminum hydroxide was one of the most insoluble salts that were up there. At least it had a very, very small KSP. And so in a neutral solution, in the absence of much H plus or much hydroxide, this remains true. However, if we have an acid or a base, this thing is going to become a lot more soluble. And so that's because this is amphoterism that is present in aluminum hydroxide, we should expect the solubility to go up when it's at a low pH or a high pH. Now, this isn't the only species that's subject to this. Zinc hydroxide, chromium hydroxide, tin hydroxide, and lead hydroxide are all stuff that we expect to exhibit similar behavior. So in this slide, you see a graph of the solubility of aluminum hydroxide as a function of the pH. And what we see is that on pHs from 4 to 10, the aluminum hydroxide is essentially insoluble. However, at our more extreme conditions, whether it be very basic above a pH of 10 or very acidic, meaning below pHs of 4, we see that solubility shoot through the roof and aluminum hydroxide becomes much more soluble. And so this amphoterism is making it much more soluble at those extremes. Another important thing to consider is the precipitation of ionic compounds. And so the question we want to ask ourselves, if we mix some calcium chloride and with some sodium fluoride, is it going to form a precipitate? And of course, if you added a lot of either, you're probably going to get a precipitate. But if we add just a sparingly small amount, is some precipitate going to form? So the equilibrium between these two is calcium fluoride going to calcium plus 2 fluorides. And this is what we began with on this particular lecture. If we go ahead and write their KSP, it's of course just calcium times fluoride squared. And that's what the KSP value is pertaining to equilibrium. Of course, we can look at this using the reaction quotient, which we haven't looked at in a little bit. And so remember, the reaction quotient is the same thing as same expression as our equilibrium constant, but it pertains to any time in a particular reaction, not necessarily at equilibrium. Now, because we like to make things difficult, we give it another name. Even though it's exactly the reaction quotient, we're going to call it something different. We're going to call it the ion product in this particular case, but it functions and acts exactly the same way as the reaction quotient. So, in the same way, if the ionization product or Q is greater than KSP, then the way that the reaction will reach equilibrium is by precipitating more salt or moving to the reactant side, just as we had treated Q in the past. If the ionization product or Q is less than KSP, then the solution isn't saturated and no precipitate will form. And if the ionization product or Q is equal to the KSP, then we're already at equilibrium and the solution is saturated. So let's take a look at a problem that's typical of this topic. So if we're asked to figure out whether a precipitate forms, let's consider if we have 0.15 liters of 0.1 molar lead nitrate and we have 0.1 liters of 0.2 molar sodium chloride. These two species are mixed and we're given a KSP for this lead chloride that is 1.2 times 10 to the minus 5. We're asked to figure out if it forms a precipitate. So we probably want to go ahead and write the reaction equation there. And then next we're going to go ahead and figure out what the number of moles of lead nitrate that are actually present. And so we know we have 0.15 liters of 0.1 molar. That gives me 1.5 times 10 to the minus 2 moles of lead nitrate. If we go ahead and look for the sodium chloride, we have 0.1 liters of 0.2 molar. That gives me 2 times 10 to the minus 2 molar, or moles of sodium chloride. If I want to figure out the concentrations, I got to divide it out by the final volume, which is 250 milliliters or 0.25 liters. That leaves me with a molarity for the lead at 6 times 10 to the minus 2 molar. And for the sodium chloride, doing the similar approach, I end up with 8 times 10 to the minus 2 molar for the chloride concentration. Go ahead and looking at the ionization product, which remember is exactly the same as Q, we end up with a value of 3.84 times 10 to the minus 4. That's a number that is greater than the KSP. If that is true, then we expect in order to reach equilibrium, it will have to precipitate out some of the lead and some of the chloride. And so it's going to form that salt, lead chloride, since that ionization product is greater than the KSP.